So the aim of this podcast is to give you the opportunity to try to prove the following four identities in vector calculus. And just on the notation, I'm assuming here that A and B are vector fields and that phi is a scalar field and that these are differentiable fields. So what I suggest you do is you write all four identities down with paper and pencil, and then starting with the left hand side, try to show that this is equal to this, etc. And then after you've done that, you can check the answers by playing more of the video. So what I would very strongly suggest you do is do not immediately look at the solution, but try to solve the problems yourself, because that gives you feedback on what you understand and it's the right way to approach mathematics. So please pause now. Welcome back. Let's look at the solutions, and I'm going to start with this identity here. So here is the solution for the first identity. So we have a vector field multiplied by a scalar field, and that means that all of the components of A are multiplied by phi, and we're calculating the divergence of it. So in 2 dimensions, and the generalization to 3 dimensions or higher is, I hope, very clear. In 2 dimensions, the divergence is going to be the derivative with respect to x of the component in the x direction of this, and that's going to be phi times a1, using the notation that the vector field is a1i plus a2j. And then the second term in the divergence is the derivative with respect to y of the component of this vector field phi times a in the y direction, and that's going to be phi times a2 in this notation that I'm using for a. So we've just got to calculate these derivatives, and we're going to have to use the product rule. So here we're going to get 2 terms where we differentiate phi and where we differentiate a1. Similarly here, the term where we differentiate phi and the term where we differentiate a2. And I've written these 4 terms out here. So what we do now is we gather similar terms together. So we're going to put together the terms where phi is differentiated, that's this one here multiplied by a1, and this one here multiplied by a2. So we just write those 2 together, and then separately we add the terms where we don't differentiate phi, but we differentiate a1 or a2. And both of those terms are multiplied by phi, so we can pull that out as a common factor, and we have phi times dA1 dx plus dA2 dy. And this, I hope we recognize as the divergence in 2 dimensions of a vector field A. What about these terms? Well, this is also something we can write as a scalar product of 2 vector fields. One of them is the gradient of phi, so it's d phi dx in the I direction plus d phi dy in the j direction. So that's the gradient. We take the scalar product of that with a1i plus a2j, in other words, our vector field A. And just to check, when we take the scalar product of that, we're going to get this multiplied by that, and that's exactly what we have here, plus this multiplied by that, and that's exactly what we have here. So this can be rewritten as this scalar product. So what we see is that the divergence of a scalar field multiplying into a vector field can be rewritten in this way. So I finally just write it out. This is the gradient of phi, and it's the scalar product of this gradient with the vector field A, plus our scalar field phi multiplying the divergence of A. And that was the identity that we were required to calculate. So we just wrote it out, and then we used the product rule, and then we put together the terms where similar fields were being differentiated. So here the terms where phi was being differentiated, here the terms where the components of A were being differentiated. And then from our knowledge of the gradient and the divergence, we were able to rewrite these in this way. So with that, we'll move on to the second solution. So the next identity required us to work out the divergence of this vector field, which was the vector product of A cross B. So we remember the definition of a vector product, which can be written in this way here, and then we just expand it. So we're going to have in the I direction for this vector field A2B3 minus A3B2, that's written here, and then as we go along here there is a minus sign, J, and then this times this minus this times this, and that's what we have here, A1B3 minus A3B1 plus, and then it's K, A1B2 minus A2B1, that's what we have here. So we're able, from the definition, to write this out. We now want to take the divergence of this vector field here, and we remember the divergence of some field that I'm calling C is just the derivative with respect to x of the component of C in the x direction plus the derivative with respect to y of the component of our vector field C in the y direction, and similarly we had the derivative with respect to z of the component of C in the z direction. And we have these components here for this vector field. So it's d by dx acting on this, minus, let's not forget this sign, the derivative with respect to y acting on this, plus the derivative with respect to z acting on this. So what we're going to have to do now is, just as in the previous exercise, to use the product rule, and for each one of these terms when we differentiate it we're going to get two terms where we differentiate A and the other term where we differentiate B. Now because the screen size isn't huge here, what I'm going to do is I'm only going to write down the terms where we differentiate A2, A3 or A1, and I'm going to claim that once I know how to write those terms, I can write the other terms very easily indeed. And here is my argument for it. This vector product, A cross B, is anti-symmetric if I swap A and B around. So A cross B is minus B cross A. So whichever terms I get with A in one way being differentiated multiplied by B's, I'm going to get the same terms but with a minus sign because of the anti-symmetry if I swap A and B around. So let's work out this differentiation, and as I say I'm only going to look at when I differentiate the A's. So here I'm going to get the derivative of A2 with respect to x multiplied by B3, so that's this times this, and then here there's another B3 and I'm going to get the derivative of A1 with respect to y, and there's a minus sign. So I get these two terms multiplied by B3. B2, because here and here, and I'm going to get minus the derivative of A3 with respect to x, that's written here, and I'm going to get plus the derivative of A1 with respect to z, and I'm going to write that plus as minus minus. So I've written that in this way. And similarly, the terms multiplied by B1, which come from here and from here, are going to give me this. So we look at this and we recognize that these terms here are terms that you would get in the curl of A. So the curl of A, written in this way, if we expand it, the component in the I direction will be dA3 with respect to y minus dA2 with respect to z. etc. This is what we get if we expand it out. So now if I look at that, this, for example, is a component of the curl of A, and it's this component. This and this are the same. This is the component of the curl of A in the z direction, and it's multiplied by b3, the component of B in the z direction. And when you look at the rest of this, you will see that all of these terms are the curl of A dotted into B. So we see that what we have here is the scalar product of the vector field B with the curl of A. And the other terms that I've not written down, where B is differentiated, I claim by symmetry I can just write a minus sign, because A vector product with B is minus the vector product of B with A, and then I just replace B here by A and A here by B. And if you're not sure about that, why not just write out the equivalent terms, use this definition but with B here instead of A, and see that you do get this. So again, what did we do here? We looked at this in terms of the definition of the vector product, expanded it out. We're going to take the divergence, so we know how that works and how to differentiate things. So this is one of the terms. And generally speaking, when we're working out derivatives in vector calculus, it's often very helpful to try to put together terms that are similar to other terms. And what I've done here is I've grouped together the terms where the components of A are differentiated, and were I to write this out, I would be writing out the terms where the components of B are differentiated. And then we just recognize that these are components of the curl of A, and that we're working out here a scalar product with B. So that is the identity that we wanted to show. With that, we'll move on to the next exercise. So the next exercise is to calculate the curl of a vector field multiplied by a scalar field. So again, a scalar field multiplied by a vector field is a vector field overall. And what we do is we say the definition of curl is to calculate it in this way. These are the components of the derivative, the nabla or del operator, and the components of phi a are phi a1, phi a2, and phi a3. So we just expand this in the standard way, and we have now to calculate the derivatives. So again, for each term we would use the product rule. Half of the terms we're going to be differentiating the phi's, and the other half of the terms, phi is just going to sit there multiplying and will not be differentiated. That's what the product rule tells us. Now, if we don't differentiate phi, if it just multiplies everything, we could pull it outside, and what we would have would be the curl of A. So all of these terms, if I pull the phi through the derivative and don't differentiate it, it's just phi times the curl of A. And again, if you're not sure about that, write this out, calculate using the product rule, and put together the terms where phi is not being differentiated, and you will see that you get this. So those are the terms that you will get. The other terms are when you differentiate phi, and those derivatives are going to be multiplied by components of A. So what you're going to get, for example, is I times the derivative of y on phi a3. So you're going to get the derivative of phi with respect to y times an a3, and that's here. And then from the product rule, you're going to get phi times the derivative of a3 with respect to y, and that's this term where I've pulled the phi outside. So these are the two sets of terms. This, I think, is easy to identify. Let's look at this. So what we have now is we have something that looks very much like a vector product, but the phi scalar field is being differentiated. And if you look at that for a moment, you can convince yourself that this is just this determinant here. So for example, if we expand this, it's d phi dy multiplied by a3. So the second row here are the components of the gradient of phi. So the gradient of phi in the I direction is d phi dx, in the j direction it's d phi dy, and in the k direction it's d phi dz. So what we have here is a vector product of the gradient of phi with A. These are the components of the vector field A. So this first row here is phi times the curl of A, and then we add to that this, which is the vector product of the gradient of phi with A. And that is the identity that we wanted to show. So with that, we'll move on to the next exercise. So in the final exercise, we want to calculate the curl of a vector field A. So let's start off by calculating this and then calculate the curl of it. So the curl of A is, we recall, defined in this way. So we just expand it and we obtain that the components of the curl of A can be written in this way. And now we're going to calculate the curl of that. So we just expand a determinant in the same way. So the first two rows look the same, but now for the components of the third row, instead of A1, we have dA3 dy minus dA2 dz, and instead of A2, we have minus dA3 dx, and then minus plus dA1 dz, etc. So now we expand this, and I'm only going to write out the term in the I direction and leave the rest for you to work out. You can convince yourself, I hope, by symmetry, that everything we see here is going to show us the answer. So what we do is, in the I direction, it's the derivative with respect to y of this minus the derivative with respect to z of this. So the derivative with respect to y of dA2 dx is a second derivative, written this way, and then we have minus, and it's the derivative with respect to y of that, which is already being differentiated with respect to y, so it's the second derivative of a1 with respect to y. Here there is a minus sign, but there's a minus sign there already, so that becomes plus. So it's the second derivative of a3 with respect to z and x. And then minus this and this gives overall a minus sign, and it's the second derivative of a1 with respect to z squared. So it's a1 is differentiated twice with respect to z. So this is quite interesting. We have two terms here which are negative, and they're both second derivatives with respect to the variables here z and here y and here z. And we have these mixed partial derivatives. So if we look at that, we are, I hope, reminded of the Laplacian operator. And the Laplacian operator is going to be the second derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to z. Now, we don't have the second derivative with respect to x here, but we can always add it and subtract it. So in this brackets, we're going to add 0, but we're going to add 0 by adding this and subtracting this term. So let's think about the term where we have this with a minus sign. Well, that's going to give us minus d2a1 by dx squared, and we've already got minus d2a1 by dy squared and minus d2a1 by dz squared, so that is the Laplacian operator acting upon the component a1 of our initial vector field. And then the remaining terms are this term, and the term that we have added, this with a plus sign. So let's look now at these three terms. By equality of mixed partial derivatives, we can pull out in each case a derivative with respect to x. Here we can reverse the ordering, pull out the derivative with respect to x, and again here reverse the ordering, pull out a derivative with respect to x, and then we'd have the derivative with respect to x of dA1 dx plus dA2 dy plus dA3 dz. But that is the divergence of A. So let's pause and see what we have here for the I component of the curl of A. So in the I direction we have the derivative with respect to A of the derivative with respect to x of the divergence of A minus the Laplacian acting on the component of A in this direction. So we can see that we would expect to have in the j direction the derivative with respect to y of the divergence of A minus the Laplacian of A2. And then in the k direction we'd have d by dz of the divergence of A minus the Laplacian of A3. So IA1 plus JA2 plus KA3 is the vector field A, and in each case with the Laplacian acting on it. So those terms are going to give us this. The Laplacian is a scalar operator here, d2 by dx squared plus d2 by dy squared plus d2 by dz squared, and all of those three sets of two derivatives are acting upon each component of A, just as we see here for the component in the x direction. And these terms here, well, this is in the I direction, the derivative with respect to x on the divergence. In the j direction, we've said we're going to have the derivative with respect to y of the divergence. And we recognize that this is the gradient of this divergence. So this is a vector field. Here we have a vector operator, the gradient, acting upon a scalar field, which is the divergence of this vector field. So this is a scalar, but this is a vector, making the whole thing a vector field, minus this scalar operator acting on a vector field. So if you're not completely sure how this is working, please write out the terms in the j and k directions, and I hope it will be clear to you. And with that, I'm going to stop this video, and I hope it has helped you with understanding how to prove some of the identities used in vector calculus.